In this video, we will prove that the real numbers are uncountable. So remember our key idea from before, that a set S is countable if its elements can be written as a sequence or list systematically. So if I'm trying to show something is uncountable, we can show that it's not possible to do that. So seeing the word not makes me think of trying to use contradiction. Right, because that was one of our strategy tips from before. If I'm going to try to show it's not possible to do this, well, let's assume that it is possible and try to get a contradiction. So to prove the reals are uncountable, we'll use something called the Cantor Diagonalization Argument. So this is a famous style of argument that's used to show sets are uncountable. So here's how it goes. I'm going to assume for the sake of contradiction that the set of reals is countable. Assume the reals is countable. Well, that means we can list its elements. We can list the elements of the reals. So I'm going to just call the first one in my list y1, the second real y2, the third real y3, and then keep going y4, keep going. Let me just list 7 of them, and then I'll put comma dot dot dot. And now what I'm going to do, for the sake of simplicity a little bit, is let's just consider the subset S that consists of the real numbers in the open interval from 0 to 1. So the real numbers between 0 to 1. That's a subset of the reals. So if I think about my list of all the reals that I have here, well, some of these are between 0 to 1. So maybe I'll highlight some of these. Maybe the second one is between 0, and maybe the third one is. Maybe the sixth one is. And maybe then a bunch of them are not, but something further down the road is, and something further down the road is. Okay, so eventually I'll have all of these things between 0 to 1, scattered throughout this list. So my elements of S, they form a subset within the list of elements that I have, all these elements of R. So if I just focus on these highlighted items that we have, well, they form a list in and of themselves. So if I just listed out these highlighted items, well, they make a list, and that means S is countable. S is countable. So I'm going to work with this set S. All right, so I'm going to list the elements of S and show that there is an element X within S, so some element between 0 to 1 that is not going to be in the list. That no matter how I try to list out the elements in this set, I'm always going to miss something. Okay, and that'll be my contradiction. So let's list out the elements in decimal form. So I'm going to call the first real within 0 to 1 R1, and the next one R2, and then R3. So notice that they all start with 0 point something, because they're between 0 to 1. And then the digits, the decimal digits that come after that, like for the first number, I call the first digit D11, the second digit D12, the third digit D13. Or like if I jump to the fourth real number in the list, I call its second digit D42. So notice that there's 2 subscripts in each of these decimal digits. The first subscript indicates, well, which real number is it coming from? So this first thing, that indicates it's coming from the first real number. And the second subscript, like here's the 3 or the 4, that's indicating which digit is it within that number. So the fact that this is a 4 means it's the 4th digit after the decimal spot. Okay, so how am I going to construct this number X? That is not one of those. So my idea is I'm going to focus on these diagonal digits. And I'm going to try to make X always be different in those diagonal spots. So what do I mean by that? So whatever D11 is, I'm going to try to make the first digit of X be different from that. So the way I will do that is I'm going to use a piecewise function and say that if that diagonal digit Dii is equal to 1. So if this happened to be 1, I need to make that first digit of X, X1, be different. So maybe I'll make it 2. Okay. And if that diagonal digit in my original list was not equal to 1, so if D11 was not equal to 1, then I'm going to make this first decimal digit of X be 1, because that'll be different. Okay, so let's see how this works in a specific example. If I look at these diagonal digits, the first diagonal, let's go to our draw mode. First diagonal digit is a 1. And the fact that it's a 1 means I'm in this top case. So I'm going to make that decimal digit of x be a 2 to make it different. So it'll start off as 0.2. The next diagonal digit is a 4. And the fact that that's not 1 means I'm going to make that second digit of x be 1 so that it's different. Okay. And the next diagonal digit is a 6. That's the same case. It's not a 1, which means I'm going to make that corresponding digit of x be a 1. So it's different. Okay, and the next diagonal digit is 1. So I'm in the top case. In the top case, I'm going to make that corresponding digit of x be 2 so that it's different. Okay, so it's going to be a 2. And this will keep going depending on what the next real numbers are in this list. But the way I'm constructing this new number x, no matter which digit I'm looking at, it's always going to be different from any of these numbers in my list in the ith digit. So in whatever that diagonal digit is, it's always going to be different from that diagonal digit. So as a result, my number x that I'm making is not equal to ri. That's going to be true no matter which one of these ri's I pick, because it's always different in one digit. So this means we have found a number x that's in my set S. It's something between 0 to 1, because it'll be 0 point a bunch of stuff, either 2s or 1s. So it's between 0 and 1. But it's not in the list. It's not on the list. And that is a contradiction. So this contradicts my assumption that S is countable. But that's going to contradict my original assumption that R is countable. So the way I'll word that is I'll say that S and thus R and thus the reals is, I'll need some more room here, is countable. And the fact that I've now contradicted that original assumption means that the set of reals is in fact uncountable, which is what we wanted to prove. Okay, so that concludes my proof. Okay, so this Cantor diagonalization argument is a really powerful and famous argument. It's very commonly used to show sets are uncountable by creating some listing, assuming it's countable, and trying to use this diagonalization type argument to construct some element that we are going to end up missing.